Okay, so welcome everyone for one of our final weeks of the course. So hopefully you're coming along with your mapping projects. Are there any quick general questions on those projects? Nope. Okay, so today we are going to spend most of the class talking about remote sensing and generally how we get those pre-earthquake data sets that you've all been using for your mapping. And I think also Rachel is going to show you just a couple hints for saving your shapefiles for the next project. Is that correct? So yeah, let's do that after the lecture. And I did first just want to go over the calendar. Can everyone see my screen?
Yes.
Okay, so today is the 19th. So it's remote sensing lecture. No preparation for this, just spend that extra time working on your fault maps. And then Thursday is going to be another breakout room discussion. So again, please come prepared with about 3 or so slides, something where you're confident about your mapping, area where you have questions that you want to discuss with your classmates and us. And then a third, just something else that you think is interesting generally in your mapping area. And then Tuesday next week, we'll discuss Salisbury reading, which is this paper here, validation of meter scale surface faulting offset measurements from high resolution topographic data. You can see many of our friends in this course, our co-authors, in particular, Ramon and Chris. Ramon, you turned on your camera. Do you want to say a couple sentences about the paper's motivation?
Yeah, sorry, I missed my mute there. Yeah, the important thing about this paper, I think there's two important things. One is the actual kind of discussion of offset channels and how they're measured and these kind of analog measurements or some semi-digital. But I think the other thing that I'm really excited about with you guys reviewing or looking over this paper is how we might adapt some of the thinking to our mapping. So, you know, it'd be nice in the future, and this is kind of what we've been pushing Rachel towards, is could we write another paper that's kind of about the validation of fault trace mapping from high resolution topographic and other data or something like that. But it's also nice because it has some discussion of bias and what does that mean in our work as geoscientists, and also tries to do some experimentation with different participants measuring the same things. And that's kind of what Rachel's working on as well, but not on offsets, rather fault mapping. So I think there's a lot of value in thinking about it, both specifically and then more broadly as an analog for what we could do.
Thank you, Ramon. And so, yeah, so on Monday next week, you'll want to send us those summaries of that paper, similar to what you did for the Landers and Electa. And then we'll discuss in Tuesday in a probably somewhat similar format to the Analecta paper. And then next Thursday, that will be our last day of class. And so I have a few topics. I'll have at least 2 people give their final presentations since they'll be in the field of the following week. And then to support Rachel's work, we'll ask that everyone complete that simple and complex mapping exercise again to help us judge what you've learned in the course and hopefully how you've improved in the fault mapping. And at ASU, the next day is the last day of the classes for the semester. And then so the next week we'll have the final presentations and importantly, very hard deadline is that your the report for your second projects, at least for the ASU students, will be due on May 3rd. So please be ready for that deadline. And then on Thursday, we'll ask you to sign up for which day you would like to present on. And we've already heard from a few people that have essentially fieldwork, which means they have to present on a specific day. All right, are there any questions? Can't quite see everyone, so please just unmute yourself and ask. Don't wait for me to call on you. No questions. All right. I assume everyone is good. Okay, so the rest of the class, next is a lecture that's can you guys not hear me well?
We could hear you.
Yeah, it sounds okay.
Yeah, go ahead. We might have to plug in the speaker here. That's fine. Keep going.
Okay, so computers are not making it easy to show you guys things today. Okay, hopefully you can see the title, pre-rupture datasets, question mark, how do we get them? So today we're gonna discuss essentially how we get those pre-rupture datasets that you guys have been using. So this lecture is essentially background on several different types of remote sensing. So anyway, please, if you have any questions as I go through, don't hesitate to interrupt. Again, I can't always see the questions. So just unmute yourself and ask. So just wanted to give you a review of the which type of data set went with which area. So for the, we'll then discuss each of these data set types in a little bit more detail. So for example, the shutter radar topography mission, which is 90 to 30 meter topography, use those for the neuromapping as well as for the data quality projects, which include Wasatch, San Andreas, and New Zealand. Many of the data sets or many projects, you've also used LiDAR, for example, for Napa, EMC, Wasatch, San Andreas, and New Zealand. Structure for motion has been used, for example, the quite old data for Bora Peak and Denali, and then for much newer data from the San Andreas Fault. And then stereophotogrammetry is used to generate the Ridgecrest data. And so for all of these pre-rupture mapping data sets, we've had to get data that was acquired before the earthquake. And so this is challenging. So it requires that someone had to have the foresight to collect the data, the funding to collect it, whether or not it was funding specifically for earthquake science or not. And then it's typically often fairly clever processing for those older data sets. So for example, the Bora Peak data is collected in the 1950s to 60s, and it's only with modern technology that we can make the digital surface model that you used for the mapping. So we're going to go over these 4 data types in some detail. So this is just in another sort of summary of the data types that we're using and the wavelength of those data sets. And so some level of the data either collected in the form of visible data. So this is wavelength of 400 to 700 nanometers. And this is collecting for imagery. So what you see in the Google Earth, what we use for structure from motion topography, as well as the stereo topography. And then next bigger wavelength is LiDAR. This is mostly near infrared, so about 1,000 nanometers, although from 900 to 1,500 is a full range. And then the shuttle radar topography mission that has, it's a radar with a 5.6 centimeter wavelength. So it's just good to keep in mind the spectrum, the wavelength of these data sets that we're using, and just keep that in mind when you're analyzing the data sets and what they show. So I'm going to start with SRTM, so Shuttle Radar Topography Mission. So this in several projects. It's a very important data set, although it is lower resolution, for example, than LiDAR, but importantly, it has near global topography. So it's from 56 south to 60 north. So it covers the far majority of the mapping areas in this project. It was flown in February 2000. The first data set was released from it was 90 meter topography, which is actually what I used for most of my PhD thesis. And then in late 2015, 30 meter topography was released, which is, may seem still like low resolution, but it's a substantial increase from that 90 meter scale. So it's a radar system. It has C-band. There's several bands in radar, which each correspond to a range of wavelengths. And in particular, the C-band has a 5.6 centimeter wavelength. So the data set was collected using single pass interferometry, and that's shown here. So this here is the Space Shuttle Endeavour. And there's 2 antennas in the system. First one is on the shuttle's payload, and then the second is here, offset along this 60-degree mast. So then topography is measured based on interferometry. So the idea is that there's 2 radar images that are taken of the ground surface, one from the saddle or one from the shuttle, and then from this antenna. And then by comparing those 2 radar images and knowing how far they were taken apart from each other, we can estimate the topography of the Earth's surface. So just as a side note, this technology is fairly similar to INSAR, which is interferomic synthetic aperture radar. However, this is strictly double pass interferometry, where you have one satellite that takes images at different times to calculate how the ground surface has moved for example, during earthquakes. But you actually can't use double pass interferometry for measuring topography. And the reason is that there's too many changes in atmospheric and ionospheric properties that mean that you can't do interferometry with those two data sets quite at different times to resolve the topography of the Earth's surface. And incidentally, one of the chapters of my thesis actually focused on the impact of atmospheric noise when using this technology to measure earthquake deformation. So, any questions? Okay, so that's SRTM. So now we're going to talk about LiDAR topography. So this is an example of a LiDAR data set, no longer looking at a very earth science application, but this is the Capitol building in Salt Lake City. And here we're looking at the point cloud topography. So LiDAR data is initially processed to point cloud data. So if we zoom in, you can see all these dots, and they represent different portions of the Earth's natural or built landscape. And each dot has an X, Y, and Z coordinate system. Here, there's sometimes other data that are collected or processed along with those X, Y, and Z coordinates. So for example, here we see color. That's fairly unusual to be collected, but here's an example of it. And then these data sets are often classified. So for example, this is a post-processing where the brown points are ground and the gray points are not ground. So in this case, very likely unclassified.
Hey, Chelsea, we're
Yeah.
seeing the slide still.
Thank you. Let me share differently. Okay, let me restart. So LiDAR data, as I was saying, is originally collected as point cloud data. So here's an example of a point cloud data set in over the Capitol building in Salt Lake City. So we can zoom in and see that data set is a bunch of points. And each of these points at least has an X, Y, and Z location. So this is what the point cloud topography data set originally looks like. And the data sets will include other information. So for example, this data set includes color, RGB, which is fairly unusual. They can also very frequently include classification, which is shown here. And so the brown points are ground, and then the unclassified points here to represent the trees and the buildings are gray. Data sets often sometimes show intensity. So this is a measurement of the intensity of the laser signal that comes back to the airplane for airborne LiDAR data. You can see that there's a variety of intensity for the different, for example, the ground, the vegetation, and the buildings. So all the LiDAR data that you've been looking at for the projects was originally collected and can be viewed in this point cloud format. Are there any questions? Right. Can you see my PowerPoint now?
Yes.
Excellent. Okay. So LiDAR stands for light detection and ranging. So I take note of that if you don't already know that. And it typically be taken by a range of instruments. For example, a terrestrial LiDAR system here, or often an airplane, or even satellite data. But for whatever instrument type, platform type, the topography structure of the Earth's surface is measured as the distance by the two-way travel time of the laser pulse. So for example, here's terrestrial laser system, can measure the distance between this instrument and this target by the time that it takes for the laser pulse to be sent out, reach this target, and come back. And so that distance is then the speed of light that this laser pulse travels times the flight time divided by 2. So we're measuring the two-way travel time. Of course, for this to work, along with essentially all of geodesy, we do need very accurate clocks. So there's several parts that are key, for example, to measuring the Earth's topography using airborne laser scanning. So here is the airplane that collects the data. So it needs to have a laser to send out the active pulses, and then it needs a sensor to measure whatever signal is reflected back to the airplane. Critical, the airplane also has an inertial measurement unit, which is abbreviated as IMU. And this is critical for precision navigation. So for example, it measures the acceleration and velocity of the aircraft, which then along with the GPS, critical for knowing where the aircraft is and how it's flying, which are used to georeference and locate each point on the ground. So, and then we're going to now go into the data collection. So you can sort of think of this approach works a little bit as a flashlight. So if you're, imagine you're above a tree and you shine a flashlight onto the tree, you're going to see a variety of light patterns. So for example, you'll see the canopy of the tree. So for example, the top of this tree structure quite well. And so if your laser pulse, there'll be quite a lot of return of energy from this top of the tree canopy back to the sensor. Portion of the sensor will measure the trunk of the tree, although there'll be considerably less return from that portion of the tree. And then again, some of the portion of the laser will reach the ground, which is shown here, and then be reflected back up to the sensor. So this example shows an idealized situation of how a LiDAR sensor would measure a tree. So this is looking an idealized scenario where we have a nadir pulse. So that means the pulse is looking straight down onto the tree. Reality, most of the time, looking to the side. And the photons from the laser pulse are going to intersect and interact with the tree. And then some of them are going to reflect back and be returned to the sensor. So there's going to be several returns from the LiDAR signal across the tree. And so the first return, for example, likely come from here, so around the top of the tree. That will come down from the sensor and then be reflected straight back up, or come down from the laser and be reflected straight back up to the sensor. May have a second and third return that reflect off different parts of the tree. And then the fourth return is going to go all the way down to the ground and come back up. So it will take the longest time to return back to the aircraft because it travels down this furthest distance. So here this is showing a fairly similar story, but a little bit more of a realistic scenario. So I said earlier, often the case we don't have a nadir pulse. So in this case, the laser signal that comes from the plane is going to be looking at an angle, so not straight down. And in this case, often expect that the laser signal, when it comes from the plane, it's going to spread out. There'll be generally a loss of energy throughout the beam as the pulse travels from the aircraft down to the ground. The different parts of the tree, so the leaves and so forth, they're going to scatter the light, and generally very few of the photons that are released from the airplane will actually make it back to the aircraft. So for example, some of these photons are going to intersect with the vegetation, with the ground, and they'll be sent off in different directions. But we do have some portion of the photons that do return back to the detector, and those are the ones that are used to measure the elevation of the Earth's surface. And in LiDAR, general problem with a lot of remote sensing, especially active remote sensing data, is that if you have water or a different type of very smooth surface, it's easy to actually get essentially no returns from the signal because they're all reflected in a direction away from the aircraft. And in this case, roughness, either in the tree or along the ground surface, is actually quite important for being able to send enough photons back to the airplane. So here's just another example of, back to what we were talking about earlier, of these different returns of the LiDAR signal. And so this figure here is looking at the point cloud of a tree, where each return has a different color. So the first returns are red, and as expected, they reflect the top of the tree. And so in this case, the laser pulse comes down from the aircraft, and first portion of the signal is sent back fairly soon to the sensor on the airplane. The second returns are shown in yellow, and they represent both more of these inner parts of the tree, as well as some points along the ground. And then finally, the third return is green. There's fewer of them, and they represent the photons that go through the tree and then reflect off the ground and return to the aircraft.
I have a question.
Yes.
Yeah, about this one. So when it determines which return is that like a time thing or like a Z thing, or how does it determine which return it is?
So it's time as well as being able to look at parts of the signal to determine which pulses they represent.
All right, thank you.
There are other questions? Okay, so once we have those point cloud data, so X, Y, Z, the next step is to transform those three-dimensional data into a raster data set. For example, the digital elevation models that we've been using. So this is a digital representation of the topography. You can see here, there is a grid of squares. So this is a raster format of the data. And then each of these squares is a pixel. So this is representation of a continuous surface where at each of these square pixels, there is a single elevation that represents the Earth's topography. Now, important linguistic item is that these digital elevation models are not true 3D representations of the Earth's surface. They are in fact only 2.5D. So why is that true? So you can imagine if you have a cliff face to really represent this feature in 3D, you'd need a point cloud where along the cliff face, you have a series of X, Y, and Z points that represent that face of the cliff. But in this raster digital elevation format, we can't have multiple elevations at each point. So we would just have one point along that cliff face that different situations perhaps would represent the bottom, top, or middle of the cliff. And so importantly, important part of terminology is that these digital elevation models are just 2.5 dimensions. And when you look at these data sets, how you've been doing on QGIS, it is always important to reference the coordinate system. So for example, is the data set essentially the address that we use for each of the points, is that address or the coordinate reference system? For example, is it in UTM or is it a latitude and longitude coordinate system? And also we've discussed the other important thing to look at is the pixel size. So what's the dimension of each of these sides of the pixel on the ground surface? We've discussed how you can look up these different features. Are there any questions? So to make these digital elevation models from the original point cloud data, there's a variety of interpolation methods that are used. And the idea of all of them is that we take an irregular set of point cloud data, so X, Y, and Z, and then we represent that data along a grid. For example, the raster grid I showed on this slide, where we have this set coordinate system or set pixel size, and each pixel has one elevation value. So there's several different ways that you can grid the elevation data to make these raster data sets. So for example, there's inverse data weighting. And in this case, say you are looking at the elevation value for this area, for this point, then you would look at all the elevation values that are within a certain distance. And then the value here is an average in some sense of all the elevations within a distance, with the closest elevation value giving more weight to the value that you use in the raster data set. Several other approaches, for example, natural neighbors, nearest neighbors, you just would take the closest point and assign that to represent the elevation of that particular pixel. Interpolation methods, there's kriging and splines. And then probably the most common one is TIN, which stands for triangular irregular network, where the point cloud topography is represented by a series of triangles, which are then gridded into a raster topography data set. So for example, here's just an outline of how that happens. So we take these original point cloud LiDAR topography points. And in this case, we apply the triangular method. So then the intermediate product is a 10, where again, we represent the topography by a series of triangles, this intermediate step. And then the final step is to do an interpolation to generate a digital elevation model. So if you go on to Open Topography, you can experiment with different gridding approaches for how to transform the point cloud data into digital elevation model rasters. And several of those examples are shown here. So for example, we can take the maximum elevation within each grid cell or pixel, and that's shown here. And in this case, we'll often include, or the topography will represent top elevation of tree canopies. And so you can see that this roughness here represents the vegetation along the landscape. Z mean here represents an approach where you take the mean value of each pixel. Z min is an approach where you take the minimum value of all the elevation points that cover that pixel. So in this case, we compare Z min to Z max. See that Z min is much closer to representing just the bare earth. And so there's a lot less roughness. we see that a lot of the vegetation has been removed. In this case, there's the ZIDW, which is the inverse distance weighting. So again, that's where you essentially take a weighted average of nearby points. And at least at this zoom level, it looks fairly similar to the mean value. So these LiDAR data sets are often flown with a on an airplane that will fly in strips. So for example, in this data set, the plane may have flown first to the northwest, for example, and when it meets the end of the intended data set area, it will turn around and it'll fly back to the southeast. And when it's flying, it's continually taking data along these swaths. And we can look and see this map to learn about the patterns of these swaths. So this map, the colors show the shots, so the number of pulses emitted from the aircraft as it collected the data, which we see red is high, blue is low. So we see first that the number of shots does vary quite a bit along the data set. And in some of these areas, the number is quite higher. So this represents an area where we had an overlap of the flight path in the two directions that the aircraft flew. And then in these lower areas, they were imaged only along one of the flight paths of the aircraft. So one of the challenges of processing and visualizing LiDAR data is to make sure that the data acquired along these different swaths are well aligned. And so this requires that you have very good data collected by the GPS and the IMU so that you can correctly determine the location of each of the points on the ground. However, if you go back particularly and look at older data, you'll find that there are problems or errors in the location of the points along some of the swaths. And so essentially, some of the swaths are offset vertically up or below from some of the other swaths. And so that example is shown here, where this, so we get this line here. It's very sharp discontinuity in the LiDAR data. If you were to come here, you might just immediately say, that looks like a fault. It's a clear quaternary scarp that goes through that field. But it turns out that this is actually an artifact from the LiDAR data. So in this area here, we see this stripe pattern, particularly these sort of north-south or up vertically oriented stripes. And this represents a corduroy pattern where the topography data collected on these two swaths don't exactly line up with each other. And then along the boundary of that swath, of the overlap in the swath, you get this very sharp discontinuity. And so in fact, is just an artifact of the data. It doesn't represent a quaternary fault scarp. And so this is just a point that when you're looking at LiDAR data, for that matter, any remote sensing data, it's quite important to understand the errors that are in the data and how they could impact how you interpret the data. So for example, to not have this error, you may want to make a plot like this that shows the point count or the shots, and just understand that they have this northwest orientation, so that it can give you some skepticism, or make you careful, make you be a little careful before you interpret faults with a northwest orientation, particularly if you see this corduroy pattern bounding one side of the fault. Are there any questions?
I'll just comment to help break things up. Maybe people wake up a little bit. So this, you can see who wrote this. This is Tryman, Perez, and Bryant. So these are California Geological Survey staff doing what you guys are doing, mapping faults. And this was something they realized they're sort of teaching themselves as the LiDAR was becoming more and more available. You see the date 2010. So so they, dug into the data and checked that they weren't seeing some very pretty little scarps.
All right, so I just wanted to, at this point, review briefly some terminology that we talked about earlier in the course. Just looking at Critical Zone Observatory in central Pennsylvania. I want to review the terminology digital terrain model and digital surface model. So a digital terrain model is a case where we've removed vegetation and built structures so we can just see the built earth. And you can generate this elevation, raster elevation model using ground points only. Then this image is looking at the same area. This is a digital surface model where I've left on the vegetation. So digital surface model is essentially represents the highest portion of the landscape. So it's the top of the canopy as well as the top of buildings. And so these two areas do look quite different. And again, we've discussed in this class the value of producing both digital terrain model as well as digital surface model. For example, to see how the vegetation varies, for example, along faults, but also to be aware that sometimes the original LiDAR topography are poorly classified. And in this case, it can be quite helpful to look at both of these products. That's the portion of the presentation on LiDAR. Are there any questions?
Just one thing, Chelsea, this is Rich. Can you comment on like who does the processing? How automated is it as far as picking first and second and third returns, and how quickly can that be done? There was a couple questions in your class about that.
So the return number, that's all done by the vendor, and you need the original LiDAR waveform data to do that. So by the time you get the point cloud data, it's very unlikely that you would be able to redetermine the point, the return number of the data set. The vendor also does the point classification. So at the very least, that's ground and unclassified. But usually it's a few other classifications such as buildings, different types of buildings, water, and so forth. Ideally also done by the vendor, although I found that there's some utility for reclassifying points. For example, if they weren't done all that well by the vendor.
Another thing to add on the classification is, to the degree that it's done manually, sometimes it's done by different groups. They'll, for a big survey, a vendor might have a team of staff who are doing the classification and the checking. And so sometimes even in the same terrain, the classification quality will vary or the sensitivity will vary. And so if you look at like sort of point counts of veg, you can have these tile boundaries where it was clearly, staff number 1 did 1 row of tiles and then staff number 2 did the other row, and you have this heterogeneity that's kind of artificial. And so that's it's not very common of an issue because usually the quality is okay, but it does point to what's going on under the hood. There's a company called NV5 there in Seattle, and I heard they have like a whole 20 staff. That's their main job, is just looking through data and checking the processing and then pumping them out.
Another thing is usually there's a survey crew or something that'll come later and ground truth the points so they can make sure, we did a 1 kilometer swath all across Alaska along the highway system, and they were surveying for like 2 months to ground truth with differential GPS a bunch of different points to make sure the classification of the ground was correct and in the proper location and stuff.
Yes.
That's right. And I don't know, Chelsea, you're going to talk about USGS LiDAR base specs.
No.
Is it worth that? Yeah, so we won't say too much, but what's that?
Go ahead, and then I do have SFM still.
Okay, I'll do it real quick. But as Rich said, there's quality to the LiDAR data, and so quality is measured by these tests of, is the point where it's supposed to be in the LiDAR, and how we check is by manual survey in the field. The other thing is the point counts, the point densities. And so the USGS has these different levels. So you'll hear, level 1, level 2, level 3. And so these are specifications that the vendors have to reach. And they, of course, charge differently depending on what's being requested. But there is a kind of a quality standard out there.
Yes. Just getting it, but it's okay. Let's move on. Actually, yeah, no, this is the last LiDAR slide. So as Rich and Ramon were saying, LiDAR data have both quality, which reflects the level of essentially how well the points are georeferenced, so how well they accurately represent the ground surface at that location, and the resolution. Generally, both the quality and the resolution of these data sets have increased over time. And so that does mean that particularly for some of the older earthquakes like the Napa and the MC, you guys are working with older and lower quality data. But this example just shows how a landscape can look different with different quality and resolution data. So this top figure on the left shows about a 1 meter pixel spacing. So we do see the landscape fairly well, but we do also get some of these triangular areas, which are an artifact from that tin triangular irregular gridding approach. But then this image here is a much better data set. So the pixel size is about 1/3 of a meter. And again, we can resolve the topography much better. And some of these weird parts of the geometry that don't look natural have been removed. And so again, if you do see some of these weird geometric features in the data, then you should have some skepticism that they truthfully reflect the Earth's landscape. All right, so I'll probably spend the next 10 minutes discussing structure of motion, to then give Rachel a few minutes to discuss the shape files. So these, next slides show structure for motion, and the idea of structure for motion is that we can take a large set of photographs, so just 2D photographs from an area, and to then generate a 3D representation of that landscape. So generate that 3D point cloud, again, from just a large number of photographs. And so that idea is shown here in this cartoon, where these red points represent the 3D model of the Earth's surface. So that could be a landscape such that we see here, for example, for EMC, Mayor-Kupika earthquake. Could also be a cliff, a house, a car, whatever feature you're interested in building a 3D model for. And then the idea is that someone takes a very large and redundant set of photographs of that area that look at that image from different location. And so, for example, here we see these 2 red points and how that they're captured by the camera in each of these locations. But they do move, the position does change based on the location, so the angle and distance that the camera is away from the 3D model. So the term structure for motion, there's 2 parts of it. There's the structure, so that includes the setup of the full geometry. So that's both the 3D model as well as the location of the camera and the camera parameters of each of these pictures that were taken. And then the structure or the motion part indicates that the camera has moved. And so it's absolutely critical that we see that 3D model from many, many different perspectives. And so this structure of motion was used for to make the Bora Peak and Denali digital elevation models from quite old USGS photography, as well as for the Southern San Andreas fault from much newer data. And so just wanted to compare how the structure for motion is different from LiDAR. So for LiDAR, we do need quite expensive equipment. So this is the aircraft and the laser system. And it works in densely vegetated areas. So for example, earlier we saw that LiDAR can really nicely see past the trees and the vegetation in Seattle to clearly show those faults. And the GPS or the georeferencing is done based on very high quality GPS and IMU. But we still do get some artifacts in location. Structure from motion requires cheap camera, can be done on a drone, an airplane, just by standing. And it uses those photographs to generate set of colored points and that ortho map, some of which given you those for different projects. And so for many projects, it is easier to get structure from motion data because you don't need a very expensive LiDAR instrumentation. So now I'm going to discuss some of the background for structure from motion. Really came from the computer science and robotics community. So this is one of the first papers on structure from motion. And you can see it came from 1978. So the idea is that structure from motion is examined from a computational point of view. The question is addressed of how three-dimensional structure and motion of objects can be inferred from the two-dimensional transformations of their projected images when no three-dimensional information is conveyed by the individual projections. And so that's essentially looking back to this original picture of how can we build this 3D image with just these 2D representations of the geometry. And then the second major advancement in this technology, which was published in 1999, is based on the Swift algorithm, which is it's the object recognition from local scale invariant features. So an object recognition system has been developed that uses a new class of local image features. The features are invariant to image scaling, translation, and rotation, and particularly invariant to illumination changes and affine or 3D projection. So this was a major advancement and essentially saying that those set of original pictures that we take, they can show features at different sizes, different areas, looking from different perspectives, and even with different amount of light and light angles. And we can still generate this 3D image of or 3D model of whatever object we're focused on. And so this is showing this for a geologic example, where, for example, we have ground and a bush here, and we can generate this 3D topography model of this area. This bush, given that the different perspectives, how we're seeing the bush, we can see different parts of it. We can be zoomed in, can be partially blocked, and the algorithm is able to overcome these different perspectives and still build the 3D model of this landscape. So this is an example. I know this is one of Ramon's example he likes of using structure from motion or yes, SIFT algorithm. So this is looking at the Colosseum in Rome, and someone took a series of photographs that were just online. So obviously different cameras from different people, different locations, different zooms. And they then took all those pictures and put them in a structure for motion algorithm and were able to generate a very nice three-dimensional image of the Colosseum. So here's just two initial papers that used the SIFT structure for motion for geoscience applications. So this first one was published in Geomorphology, Structure for Motion Photogrammetry as a low-cost and effective tool to image and measure different parts of the landscape. And then the second represents a different paper in the Journal of Geophysical Research. So if you're interested, I suggest you check those two papers out. A few more slides. Go over quickly to give Rachel time. This is now describing how structure for motion works. And the idea is that we have this landscape here and these two cameras that are looking at the ground surface. And cameras can be looking at different locations, or they are in different locations, and they're looking at different angles. And the idea is that we can use structure for motion approach to determine the location of the cameras. In this case, the distance between them. And in particular, the scale invariant feature transform. So that's that SIFT algorithm is a critical part for matching the features that are imaged along the ground despite the different certain distance between these two cameras and the location of the ground. So then so then the next step in the structure for motion is to take the matched locations of the photographs and then to generate a mathematical solution for both the ground surface as well as for the camera locations. And then this will then generate this first step of structure for motion. We get a rough picture of that structure of the area. So this includes the location of the cameras, the focal lengths of the cameras, as well as information about the ground surface. So the distance between areas on the ground, as well as relative elevation between different points. So this is, yes, the geometry is the structure, and then the different locations of the camera that refers to the motion was used in the scene. I think actually might just finish. But the idea is that, yeah, we can use the structure for motion techniques. So these are two-dimensional pictures that are taken at different locations and see the landscape from many different angles with quite a bit of redundancy to generate a truly 3D point cloud, colored point cloud of the area. It was a quick end, but I could take one or two questions and then Rachel can speak. All right, Rachel.
Do you mind enabling screen sharing?
Go for it.
So it's just going to be a quick little note about when you guys are exporting your shape files for the second project. This is going to be mostly for people who are doing a repeatability assignment or for people who are just doing more than one area. If you have your QGIS project and all of the areas are on the same project, when you export the GIR feature for it, it's going to encapsulate every single area. So even though you are right-clicking, export, save features as, and you're naming it like GIR EMC or something, it's using all of the features that you've mapped up to that point. So if I were to like zoom to layer, it's actually encapsulating all of them. So what we would like you guys to do, and I'll use this one as an example in here, is, and it's pretty easy. All you have to do is just make sure your editing is on. And if I wanted to save these GIR features for Kayakora, I can toggle editing on, go up to select features, and then I'll just click to the full extent of where all of the GIR features are. And you want to make sure the rest of the features are turned off so you're not clicking those either. And so now when you right click, export, you can save just the selected features as, and then you can name it for the specific location. And since we're doing that too, we'll want to also save the style file. And so this already has a style file associated with it, but the style file has to be named this exact same as the shape file. So you can do export and then the layer style file, and you'll name it the same thing, GIR Kayakora, and it should be fine after that. So you'll just do that for the GIR for the fault mapping as well, and then it should be good. Because now when I go zoom to layer, it just zooms exactly to that location instead of everything. And then it'll look like this too. So you'll have your EMC faults, EMC GIR, and then you'll see this layer setting style file associated with it. It's named the same. And that'll really be a lot cleaner, because at the end of the semester when we're trying to do some more analyses on the shape files, they'll actually be separate, and all of like the stuff that we have to do won't be as convoluted. That was it. And if anyone has any questions about it too, I can help them sort it out if there's problems.
Put the class video, the lecture that I just gave online, and then we'll make a separate video of what Rachel just said. But again, we would appreciate if you could help a little bit to organize those GIS files. And for example, we also saw a number of shape files that were turned in with the Landers mapping, not Landers, Wallace Creek mapping assignments. So if you're using those same GIS files from the earlier assignments, then please delete that earlier line work. You definitely don't need to turn in your Wallace Creek mapping for these main projects.
Or not necessarily delete them, just save the specific files for that area separately from the working one that you have on QGIS.
Are there any questions?
I think we're good here. Thanks, everybody.
All right.
Have a good day.